Hello and welcome to this lecture on advanced electric drives. In the last lecture, we were discussing about the principle of permanent magnet motors, and we have seen that in a permanent magnet motor, the characteristic is basically in the second quadrant. It means the motor operates in the second quadrant of the BH characteristics. So, just to recapitulate what we have studied in the last lecture, we have a circular permanent magnet material. This is the material and this is something like a ring structure. The cross section of this ring is a circle, and what we have done here, we have cut an air gap, and the air gap is of length Lg, and the cross section of this ring is A, and we have this iron path, and iron path length is Li, and air gap length is Lg, and the common flux is passing throughout this magnetic material. Now, since we do not have an external current, although we have a coil here, in this case I is equal to 0. So, there is no external current. So, since we do not have an external current, there is no external MMF. So, we can say that the MMF dropped in the magnetic material is equal to 0. So, what is MMF? MMF is the product of H and L. So, we can say that the total ampere turns is equal to 0, and the ampere turn consists of the ampere turn in the iron, that is Hi Li, and ampere turn in the air, that is Hg into Lg. Now, if we find out what is Hi, Hi will be equal to minus of Hg Lg by Li. So, we are seeing that the magnetic field in the field strength in the air gap and in the iron are opposite to each other. So, Hi equal to minus of Hg. So, what we will do right now is that we will be replacing this Hg by Bi Ai by Ag, because we know since we have a common flux, we can say that the flux is equal to flux density into area. So, we can say that phi is equal to Bi Ai. The same flux is also passing through the air gap. So, that is equal to Bg into Ag, or we can also say that Bg is equal to Bi Ai by Ag, and from this we can find out what is Hg. Hg is given by this expression, that is Bi Ai by mu naught. Mu naught is the permeability of free space, because we are talking about the air gap, it is mu naught by Ag. So, what we will do here, in the previous equation we have this Hg term in this case. The Hg we can replace by Bi Ai by mu naught Ag into Lg by Li. So, this is basically a very important derivation. Now, what does it give us? Now, this gives us that the direction of Hi and the direction of Bi are opposite to each other. We have a negative sign here, and in the right hand side we will see that we have area, the cross sectional areas Ai and Ag, and then we have the length of the air gap and the length of iron, that is Lg and Li respectively. Mu naught is a constant. So, this quantity is basically positive. So, what we have seen in this case is that Hi is equal to minus of Bi into some constant, that is, say for example k. So, it means the sign of Bi and the sign of Hi are opposite to each other. All right. So, this can happen only in the second quadrant and the fourth quadrant. So, what is the second quadrant? Second quadrant, this is the quadrant number 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. Now, in the first quadrant of the BH curve, B is positive, this is the B is in the y axis and H is in the x axis. So, we see that in the first quadrant both B and H are positive. Okay. In the second quadrant B is positive, but H is negative. It means one quantity is positive, other quantity is negative. So, signs are opposite to each other. Then in the third quadrant we see that B is negative, H is also negative, all right. And in the fourth quadrant we see that H is positive and B is negative. So, it means the operating point here, when we caught an air gap in a permanent magnet, the operating point can occur in the second quadrant or in the fourth quadrant. Now, we see that the graph is symmetrical. Now, if you see this BH curve is exactly symmetrical. You can see that we are returning like this, and again we are going from this back. So, the graph in the second quadrant and fourth quadrant are something similar. So, we can say that the characteristic occurs in the second quadrant. So, if you say that it is occurring in the second quadrant, it can lie somewhere on the BH curve, maybe somewhere here. We can say that this is the characteristic, this is the operating point. So, the operating point here means a combination of Bi and Hi. Bi is the magnetic flux density in iron, Hi is the magnetic field strength in iron. So, what we can say here is the following, that this is our Bi and the corresponding value in the x axis is Hi. So, this is our operating point. So, for discussing about the characteristic of permanent magnet motor, we will only talk about the second quadrant of the BH characteristic. Now, let us try to see little more detailed way. Now, we have already seen that Hi is given by this expression. Now, we will try to derive what is Hi by Bi. Okay. Now, if I redraw this characteristic here, what I am trying to do, I am only drawing the second quadrant characteristic. This is the y axis B, this is the x axis, that is H, and this is the second quadrant. Now, suppose the operating point here is Bi, this is the flux density, and the corresponding H is here in the x axis, that is Hi. So, if this is Bi and Hi, I can draw a line through the origin passing through this particular point. Now, we will try to see the significance of this line. Now, let us assume that this angle between this y axis and this line is theta. Okay. Now, if I am trying to find out what is tan theta is given as Hi by Bi. So, what is Hi? Hi is the field strength and Bi is the flux density, all right. So, this is what is tan theta. So, this I will write down this equation, that is equal to Hg Lg by Li into Bi by Bg Ag. So, we are trying to replace here Hi and Bi. What is Hi? Hi is replaced by this quantity. I am talking about the magnitude only. So, we will be only interested in the magnitude. So, we will forget the angle. So, I will say that the magnitude of this. So, it is Hg Lg by Li is Hi. What is Bi? Bi is replaced by this expression, because we know that the flux is the same flux is passing through the iron and the air gap. So, according to this equation, I can say that Bi Ai equal to Bg Ag. So, I can replace this Bi by Bg Ag by Ai. So, we will further do some simplification. So, what we will do here, we will again replace this Hi by B by mu naught. Hi is the magnetic field strength in air and Bg is the flux density in air. So, Bg by Hg is equal to mu naught. Mu naught is the constant of permeability. So, we can say here that this is Bg by mu naught into Lg, I will separate this out, Lg by Ag, I will bring Ag here, into Ai by Li by Bg. So, this above equation can be rewritten in the following fashion. The right hand side, Bg by mu naught into Lg by Ag into Ai by Bg into Li. Now, this Bg and Bg will be cancelled. We can cancel this quantity with this. So, ultimately what we have is the following, that is equal to Lg by mu naught Ag into Ai by Li. So, this is what we have here. Now, what is this? This is basically tan theta. Now, if we see the right hand side of this equation, which is given by this expression Lg by mu naught Ag into Ai by Li. Now, we see that this quantity is basically the reluctance of the air gap. So, we can say here that is equal to the reluctance of the air gap, into Ai by Li. So, this is the reluctance of the air gap into Ai by Li, and that is also equal to 1 by permeance. We can say that is equal to 1 by permeance of air gap into Ai by Li. So, this is equal to tan theta. So, we call it means theta is a measure of the reluctance. If reluctance is more, theta is more. If reluctance is less, theta is less. So, we call this to be the permeance line or reluctance line. We can call this to be permeance line So, we can call air gap permeance line, air gap permeance line. So, this is the significance of this line. This line gives a measure of the permeance or reluctance. Permeance is the inverse of the reluctance. So, tan theta is given by this. We can say that this Ai by Li is constant quantity. Ai is the cross section area of iron, Li is the length of the iron, those are constant quantities. So, this tan theta gives a measure of the permeance or reluctance of the air gap. Okay. Now, we can just go a little further. So, if the reluctance is more, suppose we can say that the reluctance is more. If the reluctance is more, the air gap is more. If the air gap is more, theta will be equal to a larger value. So, it means if you want to have a larger air gap, this is the reluctance in this case, and tan theta is proportional to reluctance. So, I can draw another line for a larger air gap. So, this line will be for a larger air gap. So, this is for a larger air gap. So, if I increase the air gap, I will have a line which is having larger theta. Larger air gap means larger theta, tan theta value will be more. So, here theta will be here, this is theta. So, I can say this is theta prime. I will have still larger air gap. So, I will have still larger value of theta, I can say this to be theta double prime. So, if I increase the air gap, this line will shift in such a fashion theta will be more and more. Okay. Now, if the air gap is made 0, this theta will also be equal to 0. Okay. Air gap is made 0 means reluctance is 0. So, if the reluctance is 0, the right hand side of this equation will be equal to 0. So, left hand side is tan theta, theta is equal to 0. So, it means for 0 air gap, I will have a line which is along the y axis. So, this line will correspond to 0 air gap. All right. So, it means by varying this air gap, the line can shift from a vertical position to somewhere where the air gap is maximum. All right. So, when we vary this line, an interesting thing happens. Let's see what really happens. Now, we have already seen that we are talking about the BH characteristic of a magnetic material, and we are only confining ourselves to the second quadrant of the BH characteristic. This is B and this is H. So, this is our permeance line and this is operating point Bi, and this is Hi and this is 0, the origin. Now, this point B is positive and Hi is negative. Now, suppose we increase the value of current here. So, what we have here, we have a winding in this case. In the winding, we can pass some current. Now, when the current becomes positive, Hi was negative, Hi will gradually increase. So, if Hi increases by increasing this current, what happens here? So, we will see that if Hi increases, the original curve is not traced. So, this will trace a different curve. So, it will come somewhere here. Again you decrease Ai, this will come somewhere here. So, the original curve is not traced because we have a air gap. This is the path in which we are travelling, and here if you increase this current, it will take a different path. Now, this line after something, if you again decrease this, it will come back here, and after a few cycles this line will be stabilized, and this line is called the recoil line. So, this recoil line is the line in which the characteristics move, which is different from the original BH curve. This is the original BH curve, and the recoil line is the line in which the characteristic actually moves when we increase or decrease the current. It departs from the original BH curve. So, with this background, let us go forward. Now, what about the magnetic material? We have already seen the BH curve, and this BH curve is ultimately given by a magnetic material. So, we have various types of the magnetic material. So, we will try to discuss various types of magnetic material. So, we will see that permanent magnet material and we can understand their behavior from the second quadrant of the BH characteristic. So, we have B in the y axis and H in the x axis. We have the origin. So, this is the flux density, and the unit of B is Tesla, and unit of K in this case is H is kiloampere per meter. So, we can plot the BH curve of typical magnetic material, those are available for application in electric machines. One type of magnetic material is called an Alnico magnetic material. So, we will start with Alnico. Alnico is basically an alloy of aluminum, nickel, cobalt and iron. So, Alnico is basically an alloy of aluminum, nickel, cobalt and iron. And this Alnico material are classified by various number, Alnico 5, Alnico 7, Alnico 9 and so on. Now, higher is the number, better is the material. So, this class of materials, permanent magnetic materials, are characterized by a high Br and a low Sc. So, we have high Br here, high Br means the residual flux or the residual magnetism, and low Sc. So, we have a high Br and low Sc. So, a typical material will be something like Alnico 5, and Alnico 5 will have a nature of the BH curve which is something like this. This is approximately 1.22 and this is about 60, and this curve is drawn for Alnico 5. What about other materials? So, we have Alnico 8, and Alnico 8 is having the following behavior or the following characteristics. This is about 140 in the x axis. So, high B and a low Sc. So, this is Alnico 8. So, we have drawn these two graphs, one is for Alnico 5 and other is for Alnico 8, an alloy of aluminum, nickel and cobalt. Now, let us say we will have a different material called ferrite. So, ferrite we have say here 0.4 and then we will go up to 320 in this case. So, this ferrite are also used for permanent magnet electric motors, and this is strontium ferrite. Strontium ferrite. Now, what is the characteristic of ferrite? Number 1 is Alnico, number 2 is ferrite, or they are also called ceramic magnets. They are characterized by a low Br and high Sc, low residual flux and a high coercive force. As we are seeing here that in this case we have low Br, Br is very low here, this values basically correspond to the flux density, that is the residual flux is only 0.4 Tesla, but H is 320 kiloampere per meter. This is strontium ferrite. Similarly, we can have barium ferrite. Barium ferrite is something like this, 0.24 here, and we will have something like 190. So, this is the curve for barium ferrite. Okay. And then we have another class of permanent magnet material called rare earth permanent magnet material, and they are something like samarium cobalt. So, this is the BH curve for samarium cobalt. This goes like this. samarium is a rare earth material, and the alloy of samarium, cobalt and iron is called samarium cobalt permanent magnet material. And samarium cobalt is also called rare earth permanent magnet. And these are characterized by a very high SC and Br. Both Br and SC are high. So, we can say that both Br and SC are high here, and they are also very expensive. They are very expensive. So, we can also mention this they are expensive, and they are used in those machines where we want to have very compact volume, because they have large energy density. We will be discussing about the energy density also. Now, energy density is a product of B and H. So, if we have a material having this BH curve, B is in the y axis and H is in the x axis, and this is the second quadrant BH curve. We can also plot the product of B and H. The product of B and H will be something like this. So, this is BH product, okay. B into H, we are plotting this against H, against B here. So, here we have the maximum BH. So, this is BH max, and BH gives the energy stored, the product of B and H give the energy stored per unit volume. So, if you want to have a very compact size, we have to in fact maximize BH. It means the objective is that we have to operate this motor at this operating point. So, the operating point here will be so chosen that the BH product is maximum, and that is why we have to have very high BC, BR and very high SC also. So, we can have a material with high BR and high SC, and that material is basically an ideal material, and samarium cobalt gives high BR and high SC. So, this is for rare earth material or samarium cobalt, where both BR and SC are high. So, this is the graph for the samarium cobalt. So, we can have a very large energy density having samarium cobalt, although this material is highly expensive. We also have another class of material called niobidium iron boron. So, we have another class of material called niobidium iron boron. So, this particular graph is for niobidium iron boron. So, this is another class of material NeFeB, which is basically an alloy of niobidium iron and boron. This is the best magnetic material we have, but this material also has some drawbacks. So, we will try to see that. So, this has got both high BR and high SC. So, we have high residual flux as well as high coercive force. So, this material is in fact, if you see the BH curve, looks like the best material, but unfortunately this material has got a low Curie point. Curie point is a temperature beyond which the magnetic material loses the magnetism. So, this has got a very low Curie point. So, the Curie point in this case is about, if you compare this, the Curie temperature, we can say that Curie temperature in this case is approximately 350 degree centigrade, and the Curie temperature of samarium cobalt is approximately equal to 700 degree Celsius, and about the ferrite magnets, the Curie temperature is equal to 450 degree Celsius, and for alnico the Curie temperature is equal to 890 degree Celsius. So, when we are operating this magnetic material, we should understand that the temperature of this material should be well below the Curie point. If it goes beyond that, the material will lose magnetism. So, although in neodymium iron boron the Curie point is 350 degree Celsius, the operation is restricted to 200 degree Celsius, because beyond 200 degree Celsius the metallurgical changes take place. So, we restrict the operating temperature here. In case of neodymium iron boron, we can say that the operating temperature is less than 200 degree Celsius. So, although we have very high Br and very high Sc, we have a very low Curie temperature, and hence these are preferred in those applications where we know that the temperature will not be high. So, with this background, let us go forward. Now, if we see already that we have classified this motor into two categories, the conventional DC motor having permanent magnet, and then brushless DC motor and synchronous motor with permanent magnet. So, we will try to see the field structure of permanent magnet DC motor. Now, first of all, let us see that the field structure, the field is actually in the stator. In this case, the motor is a DC motor, and in case of a DC motor, we know the armature is the rotor and the field is the stator. Now, instead of field winding, we have permanent magnet in the stator. So, the structure should be something like this. We have the armature, this is the rotor, and we have the field which is the stator. So, here we have the stator in this case, and this is the field. So, we can have north pole and south pole, and here we have rotor. Rotor is usually the armature. Now, let us talk about the alnico magnets. Alnico magnets and ferrite magnets are less expensive, so they are widely used. Now, if we see alnico magnets, we have already seen that in alnico magnets we have high Br and low Sc. So, let us write down in this case we have high Br and low Sc, high residual flux and very low coercive force. So, in this case we have a structure like this. We have high Br and very low Sc. This is the Br here and this is Sc. Now, if we plot the BH product, the BH product in this case will be something like this. Okay. Now, the product of BH gives the energy density, energy per unit volume. So, we should operate the material at its maximum BH value. Okay. So, if we cut an air gap, the air gap should be in such a way that Bi and Hi should be leading to the maximum BH product. So, this is the BH maximum, and this should be naturally our operating point. So, this is the operating point. Now, this angle is theta, as we already seen. So, we can say that tan theta here is equal to Hi by Bi, that we have already seen. This is Bi and this is Hi, and that is equal to the reluctance into Ai by Li. We have already seen this derivation little before. Okay. Reluctance of the air gap into Ai by Li. So, Ai is the cross section area of iron, Li is the length of iron. So, tan theta is equal to reluctance of air gap into Ai by Li. Now, if we are having ferrite magnet, the ferrite magnet has got high Br and low Sc. Br is fairly high and Sc is low, very low in fact. So, the maximum BH product occurs in such a way that theta is a low value. It occurs somewhere towards this Br top. So, theta is a low value here. Usually theta is low in this case for BH maximum. So, for maximum BH product, theta has to be a low value. Now, if theta is low, what about Ai and Li? Let us see that we have this expression tan theta is reluctance into Ai by Li. Now, the reluctance of air gap is a constant parameter. We cannot change this air gap length. Air gap length is almost constant. So, this air gap length is almost constant. So, we cannot tamper with or change this air gap length. So, that is almost constant. So, what we can do here, we can play with the magnet size. Ai is the cross sectional area and Li is the length of the magnet. So, in this case we can choose Ai and Li in such a way theta is a low value. It means Li has to be large and Ai has to be small. So, the ratio of Ai by Li should be small, and hence in Alnico magnet we are going for long magnets. As you have seen that the Alnico magnets should be long magnets, because theta has to be small, tan theta should be small, and air gap length cannot be tampered with, because in a machine the air gap is fixed, almost fixed. So, we can only vary the magnet size. So, to operate near this maximum BH product point, we have to have a long magnet, which means Li has to be long and Ai or the area has to be small. So, let us see some of the field structure using Alnico magnets, and we will see they are basically long magnets. So, we have a structure like this. Field structure with Alnico magnets. This is the stator structure. And what we do here, we put the magnets and the magnet are long magnets, and we have the pole shoes like this. this is the north pole and the south pole, north pole and south pole. We have the rotor. So, this portion is a magnet. And this is the pole shoe, which is made up of soft iron, and this part is the rotor. This is the housing of the stator. And what about the flux lines? The flux lines will pass like this. The flux line will start from the north pole, will pass through the air gap and the rotor core and will enter the south pole. So, this is the direction of the flux lines. Similarly, for this case, this is the north pole, the flux line will come out of the north pole, will come from the pole shoe, enter the rotor core and then return through the south pole. So, these are the flux lines in this motor, where the magnets are basically long magnets. Now, in all permanent magnets, we should remember that the permanent magnet materials are very brittle and they cannot be easily machined. Gives this kind of long magnets which can be fitted in the soft iron. So, the pole shoes are basically soft iron and the magnet is long and little curved, and the magnet is fitted in the armature, the stator housing with the pole shoe, so that ultimately it creates north pole and south pole, as we have seen. And another structure can be like this. So, we have again long magnets, and these magnets are rectangular magnets. So, what we can have here? We can have rectangular magnets. So, these magnets are like this. This is the magnet, and here we have again north pole, south pole, south pole, north pole, north, south, south and north. And this is the machine structure. So, this is the pole shoe here. These are the magnets. This is also the magnet, long magnet with long, large Li and small ai. So, the pole shoe is basically a soft iron material, and this facilitates the flow of the flux. The rotor is inside, this is the rotor. Rotor core, and what about the flux lines? The flux lines will be coming out of the south pole, north pole and entering the south pole. So, this is one of the flux lines coming out of the north pole through the pole SU and entering the south pole again through the pole SU. Similarly, here we have another flux lines from this coming out of the north pole and entering the south pole. And from this also and here also we have the flux lines coming out of the north pole and entering the south pole. So, in this case we have a 4 pole structure, and this is realized using 4 alnicomagnets, and these magnets are long magnets. Now, we can have another structure also in which we have the rotor and we have again long magnets. This is the magnet in this case, and then we have a stator core. So, we have in this case the north pole here and south pole here, we have south pole and north pole in this case, and what we have here, we have the pole SUs, and the pole SUs are made up of soft iron. So, this is the magnet we have. And here we have the rotor, this is the stator yoke. The flux lines will pass through the yoke here. So, this starts from the north pole, goes to the south pole, completes the path through the yoke in the following fashion. This is the direction of the flux lines coming out of the north pole and entering the south pole. Similarly, on the other side, we have the flux lines coming out of the north pole and entering the south pole. So, this is these are the structures of the field for alnicomagnets. Alnicomagnets are basically long magnets. Whenever they are used in electric machines, they are used as long magnets. Now, let us see the ferrite magnets. Now, we will see the field structure with ferrite magnets. In ferrite magnets, what we have low BR and high SC. Now, if we have low BR and high SC, theta will be large. If we draw the BH property or the BH characteristic of a ferrite magnet, we will see we have low BR and high SC, something like this. So, this is the flux density in the y axis, and in the x axis we have H, and this is BR and this one is SC. Now, if we plot the BH product, the BH product would be something like this. So, it means the BH product is maximum at a angle theta which is appreciably high, appreciably large. So, this is the BH maximum we have. and this correspond to an operating point which is here. So, it means theta in this case is large. So, this angle is theta. So, it means if we are having a motor out of ferrite magnets are also very widely used. We can use these magnets, but these magnets will result in high value of theta. So, if high value of theta is achieved here, so what is this theta? Tan theta is reluctance of air gap into Ai by Li. So, if we want to have a high theta, tan theta will be large. So, to have large tan theta, we will have low or small value of Li. So, it means theta is large here, which implies Li should be small and Ai should be large. So, it means the reluctance of the air gap is almost constant. So, we can have small Li and large area, large cross section area, that is Ai. So, these magnets are small magnets, not long magnets, small magnets, but having high width. The cross section area is large. So, we will try to see some of this structure using ferrite magnets. We can say that these magnets will be short magnets, but having large width. So, this is the magnet here. Something like this. So, this magnet is with north pole here, south pole here, south pole here and north pole here, and the rotor is here. So, this is the magnetic material we have, this also the magnetic material, and then this is the rotor structure, and this is yoke, this is the magnet. And what about the flux lines? The flux lines will be coming out of the north pole, entering the rotor core, going to the south pole and completing the path through the yoke. Similarly, we can have another flux line here. So, it is coming out of the north pole and entering the south pole. So, this is basically a typical field structure using ferrite magnets, and in ferrite magnets the magnets are basically short, but the width is large here. This is the width of the magnet, this is the width is large, so that the cross sectional area is large here, but the length, this length is Li, Li is small here, and this is to maximize the BH product we are having this magnet. In the next lecture, we will be discussing about the field structure with the rare earth magnetic material like samarium cobalt, and we will also see the structure of the machine when the magnetic materials are used for permanent magnet synchronous machine and also for brushless DC motor.